All right, well, our 2 minutes are up. Hello, and welcome to Chemistry 110. I'm Paul Young, and I am your instructor for this semester. There are 2 texts available. The good news is that both of them are free. They're both online. This is by Troll. Troll wrote a very nice general chemistry book and then dumbed it down and called it Intro. The concept map doesn't work. This is my book. It works. This is available free on Blackboard. This you have to go to some site, LibraryText or something. But the link is on Blackboard. Interesting site that it's on. They have found a way to steal people's books without permission and publish them. So, they got mine too. Anyway, the best way to contact me isn't by phone, but it's by email. pyoung@uic.edu or paulyoung@Triton. Office hours by appointment, online, whatever. Send me an email first, okay? If you have a question about anything. Obviously, I was at UIC, actually for 37 years. I was a full professor of chemistry and biochemistry. And later in life, I started doing general and intro. So I've been here at Triton for roughly 10 or 11 years. And it's very different than UIC. At UIC, my classes were always at 8 in the morning to 500 people. It was great fun. This is fun too, but that was great fun. As I said, Intro Chem by Tro, Intro Chem Online by me, and they're both available free. Blackboard. I hope everyone has visited Blackboard. You should. We will use Blackboard extensively for quizzes, tutorials, stuff like that. chemistryonline.com, that's my website. We'll talk about it a little bit more later. I hopefully sent, it's a new Blackboard, and I hope it's sent, I can't guarantee it, but of the packet for Chapter 1, the high point of the handout for the chapter are these things, little mini prints. First thing you should notice is they have a lot of words. The nice thing here is that means you don't have to write down the words, you can just listen. The other thing that's really neat is these are problems without solutions. So when we come to this section in the lecture, you are free to work it in space and play along in real time. It makes it work very nicely. You must have a scientific calculator. Now, the things that you need on this calculator, with EE or EXP key, you need 10 to the x and log x. Most phones have some of these functions. Most phones don't have them all. You can try your phone, see if it works. If not, $10 for a calculator is worth it. Course organization, we will have 2 cumulative exams. Cumulative means everything you've learned since kindergarten. We also will have 2 quizzes. These are given online through Blackboard. Again, the quiz on Blackboard basically will have limits in terms of either how many times you can take it or how long it's up. So please make sure you pay attention and follow the rules. Grading was basically 90, 80, 70. I will say this, if everyone in this class does exactly what I suggest, you can all get an A, no problem. If you don't, and some people don't, you won't. It's very simple. I'll explain more later. This is the Chemistry Online website. The link you would be interested in is this guy, tutorials. Tutorials are algorithmic review problems. There's a math review, and then there's sections for each of the chapters. I wrote these. They're not perfect. Sometimes they latch up. If they do, hit new problem and try again. They're algorithmic, so every time you work one of these, you will get different numbers. Let's just take a look at one of them. Exponents under math review. The problem is stated here. Basically, 3.84 times 10 to the 8 divided by 2.39 times 10 to the 20. Now, as you learned in 5th grade, when you're dealing with exponents, first thing you notice here is that this is division. If it's division, that means the exponents subtract. So, 8 minus 20 minus 12. Next, you divide the coefficients, you get 1.6. Final result, 1.61 times 10 to the minus 12. All you have to enter here is this exponent. So enter minus 12, and you got it. If you somehow did this and got the wrong answer, it would say wrong answer, but you can click show answer down here. This is what makes it a tutorial, and it will walk you step by step through the actual problem. Very good for learning. Now, you might ask or think, why in the world would I want you to do division like this? I really don't. What I want you to do is learn to use your calculator. Here's our problem. This is my calculator. It's not as nice as yours. What I would do here is simply enter the first digit, hit divided, enter the second digit, and hit equal. That's it. 1.61 times 10 to the minus 12. The reason I want you to do the exponent tutorial is, again, I want you to learn to love your calculator. In this class, we will do big numbers and small numbers all the time. You need to make sure you know how to enter them and how to do simple operations. Any questions? All right. Today we are going to do chapter 1. Actually, about 90% of chapter 1. The last 10% gets to be too much, to be honest. I tend to lecture without taking breaks, so think about that before you drink. So we can get this done in about an hour and 45 minutes. Any questions before we start? Well, chapter 1 is measurement and atomic structure. Atomic structure, we'll talk about atoms, what they are, how they're made, whatever. And measurements, we'll talk about the metric system and how to do simple measurements, things like significant figures, exponential notation, whatever. Matter. Matter is defined as any substance that has a mass. Mass is different than weight. Mass is an inherent and constant property of an object. Matter, in today's language, consists of atoms. Atoms in turn consist of protons, electrons, and neutrons. Now, protons and neutrons consist of more subatomic particles. We're not going to deal with those. Protons wind up being positively charged. Electrons are negative. Neutrons are neutral. Protons and neutrons live in the nucleus, surrounded by a cloud of electrons. Now, everybody knows what an atom looks like. It's based on the Atomic Energy Commission logo from the 50s. The only problem is that this is totally wrong. Electrons are not little balls in orbits. This is meant to be the nucleus. So according to this is what people think about when they think about an atom. You see this on Jimmy Neutron, Big Bang Theory, whatever. There are two drastic things that are wrong with this. The first is the electrons are not in discrete orbits, they're not little balls. They exist in a cloud. The cloud basically surrounds the nucleus. We, according to quantum mechanics, we can never know exactly where an electron is in this, but it is somewhere in this cloud. The other thing wrong is the nucleus. Typically, nuclei are shown as large things. In fact, they're not. This is a rendering of a helium atom. Now, here in the middle, there's a little teeny tiny red dot, 1 pixel. We'll see that even that's an exaggeration. The nucleus is teeny tiny, surrounded by electrons in a cloud. Now, atoms themselves are very, very small. A single copper penny would have 28 sextillion copper atoms. Now, this one doesn't. This has a very thin covering of copper, but if you have one of these, yeah, that's got 28 sextillion copper atoms. Because atoms are incredibly small, the things that make them up are even smaller. The mass of a proton is 1.67 times 10 to the minus 24 grams. Now, this is exponential notation. We'll talk about how to do that in just a few minutes. This number actually looks something like this. A whole bunch of zeros, and then our 167. The mass of a neutron is almost identical to that of a proton. Here we've moved our decimal over 24 places. That's where the exponent comes from. The neutron, very similar, 10 to the minus 24 grams. The electron, however, much, much less, at least 1,000-fold less. Now, this brings up an interesting thought. That is, because the mass of an atom is concentrated in the nucleus, electrons contribute very little. Atoms are essentially all empty space. Little teeny tiny nucleus having all the mass. Putting it this way, this is Wrigley Field. At least it's the old Wrigley Field. If we had an electron cloud, it was the full size of Wrigley Field. This is a golf ball. The size of the nucleus would be a golf ball somewhere in the infield. Once again, atoms are almost entirely empty space. Interesting to think about. If we have matter that has only one type of atom, that's called an element. Elements are identified by a chemical symbol. Quite often the chemical symbol is based on the name. Helium is He. There are, however, atoms that have been known for a long time, like iron, and those tend to bear Latin or Greek names. Therium is for iron, abbreviation Fe. It makes it a little difficult to recognize them all, but you will soon. Chemists tend to arrange atoms and elements on a periodic table. Now this is one classic looking periodic table, and this is one too. So, H is for hydrogen, B for beryllium, Ca calcium, C for carbon, He helium, those kind of all make sense. Magnesium, Mg, you've got to stretch it just a little, but yeah, that makes sense. The ringers look like this. Silver is Ag, iron is Fe, copper is Cu, not Co, that's cobalt. Tin is Sn, lead is Pb. These two are important. Make sure you remember those. Potassium is K, not P. P is phosphorus. Sodium is Na for natrium, an old word. Now, there are 118 elements that we know so far. I will never do something silly like give you a periodic table and ask you to fill it in. That would be stupid. But I do expect you to know the elements that we use in class. Basically, the rule is if we talk about it, you should know it. You should recognize it. Here's the starter list. H for hydrogen, write down the list. Si is silicon. P for phosphorus, not potassium, that's a K. Lead, Pb, whatever. Now, if you know these, you're going to be in great shape. But among you, there are those that are perhaps compulsive, and you want to know them all anyway. Right? Right. You can, there are sentences that have 118 words that begin with each of the elements. Yeah, you could remember that if you could recite a 118-word sentence. The easiest way I've found, if you really want to know them all, is to simply remember the song.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, titanium, nobelium, and argon, kryptonium, and radium, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Like I said, we're up to 118 right now. It's kind of a catchy song. Actually, once in my life, I sang this song for a class of 500 people at 8 in the morning. I don't do that anymore, but it was striking, let's just say that. The first periodic table was published by a gentleman named Mendeleev, 1872. He based it on reactivity and mass. He actually did a fairly decent job. He misspelled table and group, but aside from that, he did a fairly decent job. The table we use today is broken up into groups going across and periods going down. Now, I know there are 18 little slots here, but we only number groups 1 through 8. When we get to chemical bonding, you will understand why. But groups 1 through 8 are what we do. Periods we'll talk about next week when we do chapter 1, the last section, before 2. These describe where electrons live on a given atom. We can use the periodic table as a grid. Let's just look at a couple quick problems. Make sure you're catching on to the nomenclature. If I tell you we have an element, group 1, period 4. Group 1, period 4. Okay? That's not gallium. That is potassium. Group 2, period 6. Here's 2. Go down to 6, we're at BA. BA, barium. Makes sense, does it? Finally, let's do this one. Group 8, period 4. Group 8, we'll see these guys are called the inert gases. Period 4, 1, 2, 3, 4. That's K, R. Think Superman. This is krypton, not kryptonite. Any questions? As I lecture, I'm sure everybody is sitting there, of course, you're paying attention, but you're thinking to yourself, what's on the exam? Okay, let's be honest. So what I tend to do is during a lecture, I will break and we will put actual test questions for old tests and you can look at them. So let's do that. The symbols for copper, carbon, and cadmium are what? Well, we talked about copper. We said that copper was not CO, that was cobalt. So, A, B, or C. Carbon, we saw in the periodic table, is a C. So A and B. Now cadmium. First 2 letters are Ca, but that's calcium, isn't it? Cadmium is Cd. That's the answer. Which has a symbol with 2 letters. Fluorine is F, phosphorus is P, oxygen O, nitrogen N, silver is Ag. Na is what? Natrium, that's the same as sodium. Symbol with 1 letter. Well, Iron is Fe, antimony is Sb, tin is Sn, sodium is Na, phosphorus is Rp. And potassium is phosphorus is P, potassium must be K. For calcium. Any questions? Now, honestly, you'll never get questions this simple on the first hour exam, but, you know, I'll do my best. All right, let's talk about atomic symbols. Atomic symbols. In an atomic symbol, we are going to put the symbol for the element. We are going to put the number of protons in the nucleus, and we will put the mass number, which is the sum of protons plus neutrons. The number of protons for an element is the atomic number. If you look at your periodic table, there are little numbers all over it. They're sorted by increasing atomic number. Atomic number is simply the number of protons in the nucleus. And the number of protons is the one thing that defines what an element is. If it has 6 protons, it's a carbon. Doesn't matter how many neutrons it has, doesn't matter how many electrons. If it has 6 protons, it's a carbon. So, to construct the atomic symbol, mass number is the sum of protons and neutrons. Atomic number is the same as protons. We're going to put our symbol. We will do a subscript in front for atomic number and a mass number as a superscript. Simple. Let's do it. All right. Hydrogen, helium, lithium, beryllium. Hydrogen. The symbol is H. It has an atomic number of 1. That means 1 proton. We put that as a subscript in front. The mass number is the sum of protons and neutrons. No neutrons, so this is also a 1. Lithium. The symbol is Li. We have an atomic number of 3. That's 3 protons. We put that as a subscript. 3 plus 4 is 7. That's our superscript. Helium. Symbol is He. We have an atomic number of 2. That's 2 protons. Put that there. 2 plus 2 is 4. That's our mass number. And that's helium. Beryllium. 4 protons in the nucleus. Symbol is Be. When our 4 is a subscript. 4 plus 5 is 9. That's our superscript. Now that's simple, isn't it? Let's go ahead and do these. And I'll hush. Oxygen is an O, carbon's a C, potassium is a K, iodine is an I. All right, for oxygen, we start off with the yolk. Have an atomic number of 8. That's our subscript in front. 8 plus 8 is 16. That's our superscript. And that's oxygen. Potassium. Symbol is K. 19 protons, that's our subscript. 19 plus 20 is 39. That's our superscript. And that's potassium. Carbon. Atomic number 6. Symbol is C. 6 plus 6 is 12. That's our mass number. And finally, iodine. The symbol is I. Our subscript is 53. That's the number of protons. And 53 plus 74, without a calculator, 127, I think. Yes. How about that? Any questions? Well, I can promise you that in some form, on your first hour exam, you will write something like that. Okay? But sometimes I try to make it a little more interesting. Sometimes. Here is an interesting test question. Neutral element has 12 electrons and a mass number of 24. What's the period group? How many neutrons? And what's the symbol? Okay. On every exam, you're given a periodic table, so that's okay. But what's the element? The key word here is neutral. In order for an atom to be neutral, it must have the same number of pluses and minuses, right? Electrons are negative. If it has 12 electrons, it must have 12 protons in order to be neutral. So, we are dealing with magnesium, atomic number 12. So, period, that's this way, right? Period 3, group 2. If we have 12 protons and the mass number is 24, the rest are neutrons. And finally, our symbol is G, subscript 12, superscript 24, and there it is. Any questions? Well, we saw the tutorial on exponents. There are like 42 tutorials. Drove me nuts to program these all, but I did. Here's our list. In chapter 1, atomic configuration of elements and ions. Okay. If you click on this link, it looks something like this. You have 6 little spaces, 3 of them will be filled, and you fill in the rest. Our symbol here is SN. That's 10. 10 is here somewhere. There it is. It has an atomic number of 50. That means it has 50 protons. The mass number is the sum of protons and neutrons. It looks to me like it's about 160. Here our charge is +1. You don't enter the plus sign, but it's +1. Enter negative, but not 1. This means that we have 1 more proton than electrons. These are positive, these are negative. So to get a plus 1, if we had 50 protons, we must have 49 electrons. Again, if you click Show Answer, it will give you a complete breakdown of to how to do the problem. Another one, BR. BR is bromine. Bromine is in group 7, and it's right there. First thing you do, atomic number 35, 35 protons. The mass number is the sum of protons plus neutrons, 35 plus 44, 79. Our charge here is given as -1. That means we have 1 extra electron. Okay? If we have 35 protons, we must have 36 electrons. Let's do another. U. U is uranium. We look at our periodic table. Look all you want, it's not there. Well, where is it? It's actually in this little group that's down at the bottom. Now we will talk about why this is at the bottom pretty soon, but nonetheless, it's here. Atomic number is 92. That means 92 protons. Our mass number is 235. 235 minus 92 is 143. Finally, our charge. We were given that we have 92 electrons, we have 92 protons, that's the same number, it's 0. Any questions? Now let's just pretend that you're doing these and you're having a great time, okay? And so you just keep doing them, and it's great, it's fun. Eventually, you'll get to the point where this appears at the bottom. Email your instructor. Back in the old days, all you had to do was type in your email address, hit submit, and it went to me. However, in every class I've ever taught, there are at least 2 people that never figured this out. Never. They put their email address here, mine here, whatever. Never figured it out. So, instead, we are now going to ignore this, and we have moved these problems to Blackboard. On Blackboard, this tutorial, let's see, I guess it's the one that's hidden here. You practice the tutorial on the website. The advantage of this is if you get it wrong, it will tell you what you did wrong. Work with you till you get it right. If you want to do it for real, you now have to go to the Triton Blackboard site. You go to tutorial 1 of the course material, and you do it. Now, this is a quiz. Looks just like the one we just finished. We have 6 little blocks, 3 are empty, whatever. Type it in. Once you type it in, there are 5 questions. Once you type it in, Blackboard will grade it. And you can get up to 5 points. The 5 points are then added directly to your exam number 1 total. It's an oh my goodness, yes it is. These are added directly to your exam total as extra credit. Bottom line here, we are going to do 14 tutorials before the first exam. That's the potential to earn 80 points extra credit. That's a lot. Do the tutorials, you'll ace the course. Don't do the tutorials, you might not. Simple as that. Any questions? So, immediately after class, everybody is going to run to Blackboard. You're going to open course materials, and you're going to say, there's no tutorial 1. Where is it? Well, it's hidden. Yes, it is. Before you can see tutorial 1, you must go further down the page to the lab safety contract link. Looks something like this, lab safety contract. Click on it. It will ask you a few stupid questions. Hit submit when you're done, and then suddenly when you go back, tutorial 1's right there. Okay? Do that. Any questions? All right, let's elaborate a little bit on what we said about atoms, protons, and stuff like that. This represents a carbon atom. I've shown the electron cloud in 2 layers. We'll understand why next week. This is the nucleus, teeny tiny dot in the middle. It represents a carbon. Carbon has 6 protons, 6 neutrons. The symbol is C. So, our mass number is 12, atomic number of 6. We can write this for the atomic symbol. Now remember what I said about atoms. How do you know what an atom is? It's totally dependent on the number of protons in the nucleus. So if we take this nucleus and we add an extra neutron, we get a carbon atom that weighs more. We call this carbon 13. With carbon, you can do this twice. Add another neutron. And we get carbon 14. These are called isotopes. Isotopes are all the same element, but they have different mass numbers. Now, if you want to do quantitative chemistry, this is a bit of a bummer because you never quite know how many atoms are in a given mass of carbon. But actually you do, because chemists have been very clever in figuring out how to take carbon and figure out exactly the percentage is C12. Likewise, 1.1% is C13. Tiny trace is C14. If we do this little bit of math here, this is the fraction times 12, the fraction times 12. 14 is such a small number you don't need to do it. We get an average atomic mass of 12.01. If you look at your periodic table, look at carbon. This is the atomic number. This is the average atomic mass, 12.01. So if you want to know exactly how many carbon atoms you have to use the average atomic mass in your calculation. Now, the actual calculation that we just saw, I'm not going to ask you to do. That's more of a general chemistry question. But just understand that's where the average atomic mass comes from. Any questions? All right, let's turn to our periodic table. This one is not colored. The one you get on exams is not colored. This one is. Many of them are. The blue color here represents elements that are known as metals. They share certain properties. All of these conduct electricity. They're all malleable. They have what's known as metallic bonding. All the blues are metal. The yellows, these are the nonmetals. These are conductors, these are insulators. They do not conduct electricity, and they're typically brittle. The little green guys in the middle, those are our semi-metals. In between metals and nonmetals, these guys are our semiconductors. That's what makes life possible today, isn't it? Silicon, germanium, all of these are semiconductors. These guys, this is really old nomenclature, which you'll see at some places. Groups 1, 2, and 3 through 8 are called representative elements, because at one time they believed that these were the things that you would find in living tissue. They're wrong. All these guys are in there too. But long time ago, that's what it was. These guys in the middle are the transition metals. These are the regular transition metals, and these are called inner transition metals. So why are these stuck down here? Well, actually the periodic table splits right here. These elements fit here after lithium and actinium. So the true periodic table looks like this. These are inner transition elements. Now the problem with this periodic table is that it's useless. If you printed this on an 8.5 by 11 sheet, you would never read it. And nobody really cares about these guys anyway. So we just cut them out and stick them on the bottom. That's why they're there. Group 8. All of these guys are called inert gases, also called noble gases. Inert means they don't react with anything. Nobility didn't do anything either. These guys in group 7. Very important. Make sure you know these. Fluorine, chlorine, bromine, iodine. These are the halogens. Very reactive, very important in terms of the chemistry. Over here in group 1, with the exception of hydrogen, these are alkaline metals. Hydrogen gets counted because sometimes it reacts as if it's a metal. Okay. Group 2, alkali earths. Again, 1 and 2 are major players. Make sure you know beryllium, magnesium, calcium, strontium, and of course these guys. Periodic tables typically look like this, but they can take many shapes. I found one that was dear to my heart. Looks like this. Basically wrap the table in a circle. Now, why would this be dear to my heart? Back when I was taking chemistry, we didn't have calculators. When I was in graduate school, they came out with the first calculators. They did addition, subtraction, multiplication, division, that's it. No log functions. And they were $500 each. Yes. Wow. So we use slide rules. Okay? Slide rules are amazing. This is a classical slide rule equation. Yes, you can do this kind of math on this. That's how we landed on the moon. Not with calculators, with slide rules. Now, slide rules lived in a leather case that you wore on your belt, a foot long. It was a symbol that you were a scientist, yes, or an engineer. But it was unwieldy as it could be. It really got old quickly. And one day I was in the bookstore and I saw this. A round slide rule. And it fit in your shirt pocket. And you could do all the same math on it and no leather case. So when I saw this periodic table, it reminded me of my youth. What can I say? Let's do some questions. Isotope of phosphorus, mass number 32. How many neutrons are in there? This is from the periodic table. We remember 15 is the atomic number. That's 15 protons. This is protons plus neutrons. Simply subtract, and we're at 17. Here we have bromine 79. Mass number 79. It contains what? Well, this is the number of protons, isn't it? So, 35 protons, right here, the atomic number. Mass number is 79. 35, or 79 minus 35 is 44. So we're still A, B, and C. Again, the key thing here is the word neutral. In order for this to be neutral, if it has 35 protons, it must have 35 electrons. Any questions? All right. I promised you that we would talk about scientific notation. We looked at our penny. We said it had 28 sextillion atoms. Mass of a proton was 10 to the minus 24. In chemistry, we will typically deal with very large and very small numbers. That's why it's important to learn to love your calculator. To express these, we use scientific, it's also called exponential notation. This is the number of atoms in a penny, 2.8 times 10 to the 22nd. That means there are 21 zeros after the 8. Mass of a proton, 10 to the minus 24. It means we have moved this decimal over 23 places. The rules for doing it are simple. What you do is simply look at your number, and you're going to express that number as the product of two numbers. One is some integer between 1 and 10, and some number, not integer, and the other is a power of 10. 2 convert a number in decimal to scientific, you move the decimal point after the first non-zero digit. Secondly, you determine the power of 10 by counting the number of places you had to move this decimal. If you move it to the left, it's a positive. Move it to the right, it's a negative. Let's do it. 950,000. Step one, we're going to take the implied decimal point. Not a real one, but we know there must be something there. Implied. We will move it between the 9 and the 5, and our coefficient will be that. Now, in order to get this, we had to move the implied decimal point from here to here. That's to the left 5 places, so it's a positive exponent. So it's 9.5 times 10 to the 5th. That's simple. Any questions on it? Well, let's do some then. Take a moment, rewrite these guys in scientific notation. You want to use all the digits that are given, but not the zeros. Our first one here, we have a decimal point. We need to move that real decimal point between the 2 and the 5. So our coefficient looks like that. In order to do that, we had to move this 1, 2 places to the right. That makes it a negative exponent of minus 2. Our next one has no zeros. We're going to move the real decimal between the 1 and the 2. Our coefficient looks like that. In order to do this, we had to move it to the left 2 places, so it's positive plus 2. 93 million. We are going to take the implied decimal point and put it between the 9 and the 3. To do that, we had to move this implied decimal point 1, 2, 3, 4, 5, 6, 7 places. That's 10 to the 7. Doesn't matter if it's plus or minus. Here we're going to move the implied decimal point between the 6 and the 5. And we did that by moving 1, 2, 3, 4 places. And finally, we're going to move the real decimal point between the 2 and the 7. To do that, we moved it 1, 2, 3, 4, 5, 6 places to the right, so it's negative minus 6. That was good, wasn't it? Shall we do it again? Take these and convert them to decimal format. 10 squared is 100, isn't it? So we're really multiplying 2.57 times 100, 257. Ten to the minus 7. For this guy, a simple thing to remember. We're starting here, so we're going to put 6 zeros in front, and then our decimal point. Now, mathematicians don't like it when numbers look like this. They like a second zero in front. Doesn't count for anything, but it's convention. 10 to the minus 4, so 3 zeros in front. And our decorator 0. Now this one is particularly interesting. In our coefficient here, we have lots of zeros. Okay. 10 to the 4th is our exponent. So we're going to move it to the right. 1, 2, 3, 4 places. So we're here. These zeros are still real. So we would write this like this. Here's our decimal. We moved it 4 places, and these are real. What's the meaning of this? We will see when we do significant figures towards the end of class that significant figures are a simple way to tell you how accurate a measurement is. We put all the significant figures here in the coefficient. This is accurate to 0.00. This is our best guess for the last digit. So that's why it's there. The last one is trivial. Move it one spot, put a 0 in, we got that. Any questions? Well, of course there's a question. Is there a tutorial for this? Well, of course there is. Scientific and decimal notation. Let's see. We are given a number here. We have to put the coefficient here and the exponent here. Our coefficient, we're going to take the implied decimal point, move it between the 8 and 3. To do that, we had to move 1, 2, 3, 4, 5, 6, 7 places. So we'll say plus 7. Don't put the plus sign in, just a 7. Our coefficient now is going to be 4.6. We had to move to the right 2 places. That's a minus 2. Here we're going the other way. 7.1 times 10 to the minus 7. We would write our 7.1 here. And then we would put 6 zeros and then our decimal point. And it would look like that. Five point 6 times 10 to the 7. Again, don't put plus sign, I did, but you can't. We are going to have 5.6 out here. We are going to put 6 zeros after the 6, and it looks like that. One more, I think. 6.1 is our coefficient. To get that, we have to do 1, 2, 3, 4, 5, 6 places, minus 6. Any question? Now this little banner that popped up is for me to remind you, when you want to do this for credit, you will do it on Blackboard, right? Well, to enter scientific notation on blackboard. Use what's called E-notation. If we had 1700 for a number, it would be 1.7 E3. No spaces. 0024, 2.4 E minus 3. We must use E-notation on blackboard. Any questions? All right, our first lab, which we're not doing this week, we're doing it next week, has to do with measurements. The measurements that we're going to do are going to be in the metric system. Length, the standard is meter. Centimeter is what we often use. Mass is kilogram. Grams are what we typically use. Volume, cubic meter, cubic centimeter is what we typically use. Cubic centimeter is a cube that's 1 centimeter on the side. And these are called SI units, system of units, and they're commonly utilized in the sciences. We won't use inches. No, only metrics. When we are measuring the volume of a liquid, typically instead of cubic centimeters, we use milliliters. 1,000 milliliters is 1 liter, so volume of a liquid would either be liters or milliliters. Now, what do the little m's and c's stand for? These are known as metric prefixes, and they're shortcuts. If you want to write 10 to the minus 9, you don't have to write it out. You can simply use N. Stands for nano. Whenever you have an N on a unit, that means it is 10 to the minus 9. Same thing. 10 to the minus 12, 10 to the minus 6, Greek symbol mu, 10 to the minus 3, minus 2. Kilo is 1,000. Mega is 1,000,000. Giga is 1,000,000,000. Let's look at milli. Milli is 10 to the minus 3. So if I say we have 10 to the minus 3 meters, we can abbreviate that. Instead of writing 10 to the minus 3, just stick it in there. Same thing. We can also express these guys as ratios. We will use ratios in our universal problem-solving algorithm. Now we're going to do a couple of these today, but they're an extremely important method to approach mathematics and science. Very simple relationship, could do basically all the math you need, all the way to physical chemistry. It's amazing. But we'll see that in a minute. Ratio here, meters and millimeters. 1 millimeter. Remember the M stands for 10 to the minus 3. So we can simply take that 10 to the minus 3 and write this as a ratio. 10 to the minus 3 meters, 10 to the minus 3 meters, the ratio is 1. Simple. We use ratios when we interconvert metric measurements. If we wanted to convert millimeters and meters, we would write a ratio. 1 millimeter, M stands for 10 to the minus 3. That's one ratio. We can also say, if we had 1,000 millimeters, we would have 1 meter. Why does this work? This is 10 to the third. This is 10 to the minus third. If you multiply it together, it's 1. Simple. Since these are all 1, we can also just flip them upside down. So for every entry conversion, you can write 4 different ratios. If we wanted to convert meters and picometers, how would we do it? First, you would have to remember pico is 10 to the minus 12. Okay? P stands for 10 to the minus 12, and there it is. If we say we have 10 to the 12 picometers, that's 1 meter. Let's do it for meters and micrometers. Micro, Greek symbol mu, 10 to the minus 6. 1 micrometer, 10 to the minus 6 meters. If we have 10 to the 6 micrometers, we have 1 meter. One more. Nano, nano is 10 to the minus 9. Little n is the symbol. 1 nanometer, 10 to the minus 9 meters. If we have 10 to the 9th of them, that's a meter. Now, how do we use these? We will use these in this problem-solving algorithm where we look at our problem, we decide what is our given number. We do a ratio that connects our given and what we're trying to find. We multiply these together and we get our answer. That's all there is to it. Really, this will take you through P1. It's amazing. The only given or the only issue there is that the ratio you set up. Given will have units. The units of given must be in the denominator. Let's see an example. If we had meters and wanted to find kilometers, kilo is 10 to the third, and we put meter in our denominator. Do a real problem. 6,000 kilometers is meters. Think about how you would do this. This is the given. So kilometer must be in the bottom of our ratio. This is 10 to the third. So we have 2 ratios we could write, but only one will have 10 to the kilo in the bottom. So this is the one we want. Start off with our given, stick in our ratio, kilometers cancel, and we get meters. Do the simple math on your calculator. 6,000 times 1,000, 6 times 10 to the 6. Given, ratio, and what you're trying to find. Universal algorithm. We're not going to do these problems right now. Instead, we're going to do a simple version, okay? Let's just look at this list. What I want you to come up with is the ratio, grams to kilograms. Now, you know that grams have to be in the denominator. Kilo is 1,000. So for this first one, we can write this, 1,000 grams, 1 kilogram. So this is our ratio. Multiply the given by this ratio, we get 2 kilograms. Isn't that simple? Look at the next one. Micro is 10 to the minus 6. Meter is in our denominator. We're going to say 10 to the minus 6 meters, that's micro, these are the same. Multiply this by our given 0.125 micrometers. Grams and nanograms. Nano is 10 to the minus 9. Gram is in our denominator. 10 to the minus 9, that's 10 to the minus 9 too. They're the same. Multiply by 9.3 times 10 to the minus 4. We get 10 to the 5th nanogram. Two more, meters and kilos. That's simple. Kilos 1,000, we've done this. Meter in the denominator, 1 kilometer, 1,000 meters. Multiply amount, 65.8. And our last one, simply grams and milligrams. Milli is 10 to the minus 3. Grams in the denominator, 10 to the minus 3, that's 10 to the minus 3 also. Multiply 278. Any questions? We will use this as we go through the course. You'll get very good at it. All right. When I wrote my original 45 tutorials, which made me blind, wasn't easy, really wasn't easy. The coding is just a nightmare. But when I did this, I did not do metric conversion. 2 years ago, class asked me uniformly, could I do that? And so I did. This was even harder going back after all those years, but simple metric conversions, grams and kilograms. Kilo is 1,000. Our given are 3 grams. Our ratio, gram in the denominator. This is kilo. 10 to the minus 3 times 10 to the third is 1, so that works. Put it in the standard format. Given, ratio, find. 003 is our answer. One more, I think. Milliliters. Remember, that's the same as a cubic centimeter. We use those for liquids. Milli is 10 to the minus 3. Liter is 1,000 milliliters. This is our given. We have 10 to the minus 3 liters in a milliliter. And we're trying to find liters. Again, 10 to the minus 3. This is a mistake. Should be a plus. I just do this to prove to you that I make my own slides. But that gives us milliliters. Here's our problem. Given ratio, find 2.51 is the answer. Now again, when you do this on Blackboard, key notation if you need big or small numbers. Okay? Now you can also type it in 0, but you always get the zeros messed up. Use E notation. Finally, winding up our metric system. It's hot outside, right? Everyone knows water freezes at 32, boils at 212. Well, you can forget that. Those are Fahrenheit. We will never, ever, ever use Fahrenheit in this class. Instead, we will use centigrade when we hit chapter 9, will be introduced to Kelvin. Centigrade, water freezes at 0, boils at 100. Kelvin, kind of an odd scale, water freezes at 273 and boils at 373. What makes it useful is there's 100 little steps between these, and the same with these. So the size of the degree is the same. Any questions? Finally, significant figures. Like I said, our first real lab is going to be measurement. When you do a measurement in science, you need some way to tell the reader how accurate your measurement was. That's called significant figures. Let's pretend that I gave you a ruler and put an arrow on it. So, where is the arrow pointing? Well, that's 50, that's 54, that's 55. It's more than 54, it's less than 55. By George, kind of looks in the middle to me. I would say 54.5. No, it's not 54. No, it's not 55. And it's somewhere in the middle. This last digit, we're guessing. It could be 6, could be 4. It's about 5. This, we will say, is 3 significant figures. The first 2 here we're absolutely sure of. This one is our best guess. If I was to say this was at 54, that would be wrong. It's more. And if I was to say it was 54.66666, that would be stupid. Because we don't know that. We know it's somewhere in the middle. 3 significant figures. The first 2 we're sure of. The last one is our best guess. Anytime you see a measurement, the last digit is the best guess. The one area that students have issues with for significant figures is zeros, numbers with zeros. For this, you want to look at your number and decide, does it have a real decimal point or not? If it does have a real decimal point, like this one, leading zeros, that's these guys in front, they're not real. Trailing zeros, that's real. That was your best guess. This would have 2 significant figures. If we don't have a decimal point, like this guy, trailing zeros are never significant. So these guys, they go away. Again, 2 significant figures. I repeat this one because it's important. If we have zeros in between real digits, they're real. So let's just do a couple. Here's our number. We look at it and we say, decimal point, leading zeros don't count. Trailing zero, that counts. We have 2 significant figures. At 3,400, no decimal. Trailing zeros, they don't count. We're left with 2 digits, 2 significant figures. Here we have a decimal point and leading zeros. They don't count. This 0 is in between real digits, and it counts. 3 significant figures. No decimal point. That's real. This one goes. 3 significant figures. Now this is the one that's really important. 6.02 times c to the 23rd. How do you do something in exponential notation? Well, one thing you could do is convert this to decimal. Stick on 21 zeros, and you get that. But there's no decimal point, is there? These are all trailing zeros. They're gone. We have 3 significant figures. Whenever you write a number in scientific notation, the coefficient here contains all of the significant figures in the measurement. That makes it very easy to figure out what it is. You just count 1 to 3. Let's do 2 things at once. Convert these guys into scientific notation and put in the proper number of significant figures. So you look at a number, decide how many significant figures, put those down as your coefficient, and write it as scientific notation. We have a decimal point, and we have leading zeros. They're gone. This number has 3 significant figures. I'm going to move that decimal over 2 places. That'll be a minus 2, 2.57 times 10 to the minus 2. No zeros to worry about here. Going to move our decimal over between the 1 and the 2. 2 places, it'll be a plus 2. 4 significant figures, they're all in there. $93 million. No decimal. Trailing zeros disappear. So we have 2 significant figures. Going to move this over 1, 2, 3, 4, 5, 6, 7 places. That's 10 to the 7. Now think about this number here. It has a decimal point. That's the measurement. So this last zero is what? It's your best guess. Your best guess for the last digit in this measurement was a 0. It's about 0. So that means this number contains 1, 2, 3, 4, 5, 6 significant figures. They all have to be in the coefficient. So we're going to move our decimal point 1, 2, 3, 4 places, and it'll look like this. All these zeros are there because they're real. The last one is trivial. We're going to get rid of our leading zeros. We have 3 significant figures. We just move it in, and we're at 10 to the minus 6. Now, on your first exam, again, I will suggest that you will probably have a problem where you're asked something about significant figures. So, a long time ago, for a class of 500 at 8 in the morning, I decided to put this on an exam as a question because it was just kind of silly, I thought. You'd give a number and say, how many significant figures is that? So here I want you to arrange these in decreasing order. Much more interesting problem, right? Leading zeros are gone, we have 2 here. Zeros in between digits, we have 5. Decimal point, we have 6, 7. No decimal point, those go, we have 3. Decimal point, add it all up, there's 8. No decimal point, we have 3. So our winner was 8. Second place goes to 7. Third place, I'm thinking, 5. Fourth place, 1501. Fifth place, the 3. And finally, the 2. Now this really was a neat question. But when I wrote it, for some reason it didn't dawn on me that somebody had to sit and look at 500 exams and check to see if all these were in order. Yeah, that was brutal. Never done it again, but it was fun. Any questions? The significant figure tutorial is everybody's favorite because it's so simple. You are given a random number, and all you have to do is enter the number of significant figures. No decimal, 1, 2, 3. Decimal point, 1, 2, 3, 4, 5, 6, 7, 8. Scientific notation, by George, that's simple. You just count, 1, 2, 3, 4. Leading zeros don't count, trailing does. That's a 2. Any questions? Again, this is the tutorial that everybody does. It's guaranteed 5 cents. All right, there is one ugly thing about significant figures. Quite often when you are doing measurements, you're going to use those measurements in calculations. There are rules as to how many significant figures your result may have. There are 2 rules. One makes sense, the other one doesn't. Sorry. This one is the one that doesn't really make sense. If you're doing addition and subtraction, you would think you would look at your numbers, see how many significant figures they each have, and then come up with an answer. That's wrong. What you do is you look to find the decimal place. You look at how many places there are in the number after the decimal point. That defines the number of digits after the decimal in your answer. Easier to show than explain. 1.455, that's 4 significant figures, right? 3.2, that's 2. Feed these to your calculator. You get 4655. But here we have 1 digit after the decimal. Here we have 3. So we have to take this number and round it to 1 place. That's the one that's difficult to remember. The other one makes a great deal of sense. Multiplication and division. If you're doing measurements and you multiply and divide them or whatever, the results you get can be no more accurate than your worst measurement, right? Right. Therefore, what you do is simply look at your numbers, decide who has the fewest number, and that sets it for the problem. 3 significant figures, 2 significant figures. Multiply them. There's your calculator answer. You must round this to 2 significant figures. So this is 2.9. All right. You know what? We have survived chapter 1. The interesting part of 1 is going to come before we do 2 next week. So, hang on to your sheets. We're going to talk about it, but that's next week. If we did it now, I would probably pass out after 10 minutes. So, not going to do it now. Remember, here's the 5 tutorials we have. Exponent, sig fig, decimal conversions, metric conversions, and protons. 5 points for each of these added directly to your total point exam score. Remember, you cannot see these until you complete the lab safety quiz thing, whatever it is. So do that, then you can